Hello, welcome to my next video in my series about oscillators. Last time we talked about the astable multivibrator, and today we are going to talk about a derivative of that circuit called the Wien-bridge oscillator. So we start with a couple of transistors. I need some room, so let me move over here. It's transistor number 1, coupling capacitor, transistor number 2. Let's make sure our emitters are grounded. Collector resistors, biasing resistor, etc. "10-volt power supply," or 10-volt VCC, if you will. And there's our second coupling capacitor, and of course our feedback comes back in over here. So there's the astable multivibrator, just two stages of amplification. Timing capacitors which give us our delay and help with our timing, and this will produce square waves, as we say in the video. So that would be the output of one collector, and the other collector would have square waves 180 degrees out of phase with the other collector. So why does this produce square waves? Well, because it has too much gain. It just saturates and goes all the way to the voltage rails, and so goes all the way up, all the way down, all the way up, all the way down. It has too much gain, so we need to add some negative feedback to reduce the gain. So let's make these transistors more like the typical small signal amplifier. Just give a little more control to the gain. Okay, not going to do any components at this point, but there's our typical small signal amplifier, and we fed that back in and made a modification of the astable multivibrator. The question is, will this oscillate? And the answer is, if you get the gain right, yes it will. You can add these resistors here. You can't make these resistors too big because that'll reduce the gain too much. Remember, this causes negative feedback. As our current flows from the emitter into that resistor, that's going to raise the voltage across that resistor. And of course, if that voltage is raised here, that raises it at the base, so that opposes any current coming in. So that actually gives us negative feedback. The more current in, the greater that voltage, the more it opposes it. And by the way, the size of that resistor is bigger than the resistor looks. When we talk about the small signal amplifier, remember that the value of this resistor, looking from here, is the HFE of the transistor times that resistance. And so it even looks bigger. So we get a lot of negative feedback just from having that resistor there. So that adds negative feedback. And if we have just the right amount, if we start increasing this feedback, we'll notice that that square wave gets a little sloppier as we increase that feedback. But to get just the right amount of feedback to make this into a sine wave oscillator is very fiddly. If we get just tiniest bit too much, it just stops oscillating. And so it's not a very good oscillator for making sine waves. If you want to do that, you probably want to go ahead with the phase shift oscillator. But there is a modification of this that will produce nice sine waves, and it's called the Wien-bridge oscillator. So let's erase that for a moment. And here is a typical diagram of the Wien-bridge oscillator, just to show why it's called that, because people like to draw it like a bridge circuit. So here's the idea of the Wheatstone bridge circuit. We have a component here, a component there, another component here, and another component there, and then another component here. And we talk about that at a totally different time, but that's known as the Wheatstone bridge. And if we put our amplifier in here and put the right components around there, as in this drawing, we have a Wien-bridge oscillator. So let's take a look at how that works. So we're starting out with this circuit, and this will work as it is, although the working circuit I'll show a schematic of has some of the components missing, but that doesn't really matter. So what are we going to do? We want to control the gain of this, but controlling the gain alone is really not a good way to get sine waves, because as I said, if you reduce the gain the tiniest bit too far, it'll just simply stop oscillating. So what we're going to do is add some circuitry to the feedback, and this is just a different way of drawing the Wien-bridge oscillator. So what we're going to do is come back here, and we're going to add a resistor and a capacitor. And then here we're going to add just a capacitor. Notice that's in parallel with this resistor. So I'm going to remove that just to emphasize that these are working together. So let's get rid of our resistor. It's still there. It's just now we've just moved it over here just to remind us that it's working in concert with that capacitor. This resistor will be identical to this resistor, and that capacitor will be identical to that capacitor. Oh, I want to make some room here. Let's move this down a little bit, right to there. There's our resistor. There's our capacitor, because I want to come across here through that resistor, a little jump there, to there. Now, that is exactly the same circuit as this, at least as far as the way the bridge is hooked in. That is our Wien-bridge oscillator. So what's it going to do for us? Well, one thing is we're adding more negative feedback. So our signal, which normally goes to the base, giving us positive feedback, is now going to the emitter. If you put a signal to this emitter, it's going to act as negative feedback, because once again, we're adding more current to here that raises that voltage. So as this voltage goes up, this voltage is also going up. And as that voltage goes up, that causes more current through this resistor. That's going to cause a greater voltage there. So that's going to push back, causing more negative feedback. So that's one way we add more negative feedback to the circuit. And might as well mention at this point, it's still very hard to control. So typically a Wien-bridge oscillator will have something here to help control that negative feedback. Early Wien-bridge oscillators put a light bulb here. So what does that do? As we increase the current through the light bulb, its resistance increases. So it gives us more negative feedback. As we reduce the current through the light bulb, its resistance goes down, so we get less negative feedback. Now, it doesn't necessarily have to be enough power to make the light bulb light up, but just enough to warm it up. But that's also going to have a little bit of a time lag, so it won't work very well at high frequencies. So modern Wien-bridge oscillators, instead of light bulbs, you might see them, but some of them have a feedback circuit with a FET. A little more control circuitry there, but I don't want to go into that at this time. I just want to talk about the basic oscillator. So there's other ways to control the feedback, and sometimes, I haven't seen this done with transistors, and I haven't figured out how to do it. Sometimes we're going to put some diodes in the feedback loop. I'll just draw the basic idea here. And because of the nonlinear nature of those, it changes the feedback characteristics enough. If I have this drawn the right way, we'll look at it at a different time. But if I have this drawn the right way, this also will help control the negative feedback and keep the oscillator working. But that's not what I want to discuss right now. I just want to discuss the basics. But the other thing are these two RC circuits, because together they form a bandpass filter that only allows one frequency to go through the oscillator. So if we start trying to produce square waves, remember what a square wave has? Anything other than a sine wave has frequencies other than the base frequency. So the square wave is going to be the fundamental frequency plus all of our odd harmonics. Well, if we're starting to saturate and starting to produce square waves, we're starting to produce those harmonics. This will filter those harmonics out. As a matter of fact, I'm going to kind of disconnect it from the rest of the circuit right now so we can just kind of look at it by itself. Just removing these just so we can look at the filter. So we have a resistor and capacitor in series, a resistor and capacitor in parallel. Let's take a look at what this is going to do at different frequencies. At higher and higher frequencies, this has a lower and lower capacitive reactance. In other words, its number of ohms because capacitive reactance is measured in ohms just like resistance. At higher frequency, this has fewer ohms than at lower frequencies. And at very high frequencies, this is going to look like a closed switch, as will this. So now we're looking at high frequencies, where both those capacitors look like a closed switch. So let's go ahead and connect this to the base there. So what's going to happen? The current at high frequencies, they'll go through here, but it's shorted straight to ground. Basically, we have this resistor is shorted out. This simply goes to ground, 0 volts. And since there's no resistance between there, no matter how much current we get, we're not going to get a voltage difference. So now we're talking about alternating current, of course, but our voltage is 0 volts at high frequencies at the base of that transistor. Now let's see what happens at low frequencies. And at low frequencies, this is going to be a very high reactance, a lot of ohms. In fact, at very low frequencies, that's going to look exactly like what it is, 2 conductors separated by an insulator. So at low frequencies, this is essentially going to be a open circuit. Same thing here. So at low frequencies, although if we had some current flowing through here, we could get some voltage across it, but where is that current going to come from? It's going to come and be blocked by that open capacitor there. So that's going to block low frequencies. But let's look at what happens at the cutoff frequency. So if we take our resistor and our capacitor, so our cutoff frequency is equal to 1 over 2 pi RC. And so that's the frequency we want this to oscillate at. So we pick the capacitor and resistor combination to have the cutoff frequency we want by doing some messing with the math. That's not what we're going to do here, because we talk about that in the AC class. So at the cutoff frequency, we have a situation where our capacitive reactance, the number of ohms presented by the capacitor, is equal to R. And we have the same thing over here. So basically everything's equal. Well, not really, because we're talking about parallel circuit, series circuit. Let's see what happens in the end. Well, so if I draw my impedance triangle, where this is our resistance and this is our capacitive reactance, they're equal, so that's going to be a 45-degree angle. So theta equals, we're going to make it a negative 45, because since it's a capacitor, that impedance is going to give us a negative phase angle. If you're not quite following that, be sure to review the AC circuits class, but that's going to give us a negative phase angle. And that line, which is our impedance, is going to be equal to 1.414 times our resistance or times our capacitive reactance, either one. So it's going to be 1.414 times that. Over here it's a little different. The math is a little more complicated, but the end result is that over here we're going to have our impedance triangle. It's going to be almost like it's a inductor, because we're going to have a positive phase angle. There's our X sub C and our R. It's going to be a 45-degree angle, but it's going to be positive 45 degrees. And because these are in parallel, we can't just add them straight together. We have to do the product over sum, which gets really complicated when we do this. And so we're not going to do it now. We mess with that in the AC class. But the result is, but since these are equal, the product over sum formula works out such that the total reactance here is going to be 1/2 of 1.414 times R, or make it just a little simpler, 0.707 times R. And so the impedance here is going to be half the impedance there. So all of that talk just to say this, that because these are in parallel, they'll have half the impedance. So we'll just treat them like resistors now, just to simplify the circuit. Remember, this is at the cutoff frequency, so at our cutoff frequency, we're going to have a resistance here. It's imaginary. Remember, it's a full impedance. In fact, just to be realistic, have a few fewer face palms out there. I'll just call this an impedance. And we'll do the same thing over here. What's the difference between a resistor and an impedance? Is phase angle and such, but otherwise it works the same. So there's an impedance there. And because those components were in parallel, if we have a Z here, a certain impedance there, this is going to be 1/2 of that. So let's just say that this impedance came out to 20 ohms. This is going to be 10 ohms. So what do we have? Let's make a little room here just to draw what we're doing. We have to redraw a lot of stuff, aren't we? We have a series circuit, looks like a couple of resistors, 20 units and 10 units. So if you're not following this, go back to DC circuits and look up voltage dividers. Let's say we have plus 9 volts here, just to make the math easy. We're going to have twice the voltage here as we have here, and they must add up to 9 volts. So that's going to be 3 volts and 6 volts. So we have 9 volts and we lose 6 volts. We're going to end up with, so there's our voltage divider. So we're only going to have 1/3 of the voltage here that we started with. That's important because it tells us what gain we need in our amplifier. So after all of that, let's go back to our Wien-bridge oscillator. So now we're back to our filters here. So what do we say? At our cutoff frequency, the frequency we want this to oscillate at, this will be acting basically like a resistor that's twice the value of this resistor. So whatever voltage we have here, we're going to have 1/3 of that voltage here, which means that to have a gain of 1, our amplifier has to have a total gain of 3 to match our 3-to-1 loss over here. So I said all of that just to explain that little bit there. So once again, I've said a lot of things here, so let's just back up a little bit and remember that these two RC filters here act like a bandpass filter because at very high frequencies, everything goes right through here but gets shorted to ground. Very low frequencies don't make it through, but at the cutoff frequency, or desired frequency, this acts like a resistor that's twice the size of that resistor. So we have our maximum voltage here, which is 1/3 of the incoming voltage. Therefore, we have to have a gain of 3 here to make a total gain of 1. Before we move on, I want to address a couple of questions I think may come up about the feedback filter, which I have isolated on the board here. And the questions are, why are the two filter elements in different configurations? In other words, why are the capacitor and resistor in parallel here and in series there? Why aren't they either both in series or both in parallel? And the other question is, well, now that we've determined that they need to be different configurations, why do we have them in parallel here and in series there and not vice versa? So let's take a look at that. First of all, let's see why they are different configurations. So what we have is identical resistors and identical capacitors. We don't need to look at the numbers at this point, just know they're identical. Therefore, the cutoff frequency of this part of the filter and the cutoff frequency of this part of the filter are the same. So now, if they were the same configuration, let's just go ahead and put them both in series. Doesn't matter which one. We'll see that that does not matter in a moment. Let's say they're both in series. Therefore, let's say at low frequencies, the filter elements have an impedance of 1K. So we're looking at low frequencies now. And so they each have 1K at that low frequency. Now let's move that up to a high frequency and say now they have a impedance of 10K. So notice they both have the same impedance regardless of the frequency. So let's just reduce these down to a simple voltage divider because that's what it is. It's a series circuit by itself. We're going to assume that the other components are chosen to have a high impedance compared to our filter element so that it will act pretty much independently as a series circuit. So let's go ahead and draw that. So we have a voltage source coming in to a resistor, to another resistor, and to ground. and this goes on to the rest of the amplifier. So let's say this is 1K and this is 1K. What do we have? We have a voltage divider. Let's put a voltage up here. Let's just say 10 volts. So we know in a series circuit we have the same current through both components. Therefore, they have the same voltage across them. So we have current and resistance. Therefore, we get voltage. So remember, whenever we have current and resistance, we're going to get a voltage. So there is a voltage across each component. And because they are the same resistance with the same current, they must have the same voltage. And those two voltages must add up to the total voltage. So what do we have? We have 5 volts across that resistor and 5 volts across that resistor. This is something we learned way back in DC about voltage dividers. So that means if we have 0 volts here and we gain 5 volts, that's going to give us plus 5 volts here. So that's what goes on to the amplifier. Of course, we're talking about AC, but everything still works the same. It may be starting with 10 volts AC. It still ends up with 5 volts AC here, 5 volts there. 0 to 5, we get 5 volts at the middle. So if we increase this to 10K, so we've increased the frequency and caused that to go up to a higher impedance. And so now what do we have? Well, we still have the same resistance, same current through both resistors. We don't know what that current is. We don't need to know. We just know it's the same. Therefore, we have the same voltage. And so at high frequencies, we still get the same 5 volts there. So if these are the same configuration, let's draw them back as a capacitor and a resistor. Regardless of the frequency, they will both have the same impedance. So at low frequencies, they may have one impedance. High frequencies, they may have another impedance, but they will be the same at any particular frequency. So this will not even act as a filter. No matter what the frequency, we will get the same voltage division. So whether we make them in series or in parallel, if they are the same configuration, we will not get any kind of filtering, because no matter what the frequency, we will still have the same voltage division. It's still same impedance, same impedance. What's the rule about voltage dividers? If the impedance is the same, the voltage is the same. Therefore, we start off with 10, we lose 5, and there's 5 volts there, no matter what the frequency is. So they have to be different configurations. So the next question is, why do we have it like this? We have a series configuration followed by a parallel configuration. And we noted that after the mathematics, we find that this is going to have about half the impedance of that. So let's change the voltage. We'll keep that at 10 volts. So let's make it 9 volts just to make the math easier. So we're going to have 6 volts here and 3 volts there at the cutoff frequency. So now we're looking at the cutoff frequency. We're going to have a higher impedance here and about half that impedance there. Therefore, we have about twice the voltage there as there. Therefore, this becomes about 9 volts. That becomes about 3 volts there. And so we have to have a gain of 3 to have an overall gain of 1, because as we're feeding back, we lose 2/3 of our voltage going across this part of the filter, have only 1/3 left at our cutoff frequency. Therefore, we have to have a gain of 3. So why don't we flip that around? Now, we flip that around. We only lose 1/3 of our voltage. So now we only have to have a gain of 2. Well, it doesn't really matter. I mean, what's the difference between having a gain of 2 or a gain of 3? It doesn't really change it, so that's not really important. So once again, why do we have the bottom configuration in parallel and the top configuration in series? I'm going to redraw this the way we draw it in the regular circuit to explain that, because that helps us see how it acts as a filter. So our feedback is coming in. We have our series filter and then our parallel filter. course, this goes to our amplifier. And now let's take a look at what happens at high frequencies. Okay, so at high frequencies, this is going to essentially be a short circuit. So we'll show that as a closed switch. Same thing here. Closed switch. So this resistor is essentially shorted out at very high frequencies. As we get closer to the cutoff frequency, it becomes more of a resistor. But let's just look at very high frequencies to simplify it. So we have a short circuit in parallel with a resistor. What's the total resistance? The total resistance will always be lower than your lowest resistance. So our total resistance is, well, it's a short circuit, 0 ohms. So all of our high frequencies get shunted away. And we want to do that because the high frequencies are going to contain our odd harmonics, which are what gives us a square wave in a sense. Without this filter, this is going to tend to saturate and give us square waves. We basically have an astable multivibrator, and those square waves contain all of the odd harmonics, which are higher and higher frequencies. So if we can filter out those high frequencies, it's going to cause this to round off on the leading edge. So we want to eliminate those high frequencies. Let's see what happens if we put these in series instead of parallel. Here's our capacitor, which looks like a closed switch, and there's our resistor. So now we have some amount of resistance there. If we have current flowing through resistance, we get voltage. Therefore, at the high frequencies, we don't short out all of our high frequencies. We do get some voltage here. Therefore, we're not eliminating those high frequencies, and we're going to tend to saturate. So we need to have this not in a series configuration where we have the capacitor looking like a short circuit at high frequencies in series, because then we still have resistance there, which means that we're going to still develop some voltage even at high frequencies. Therefore, we're not filtering those out. So we need to put the capacitor in parallel with the resistance in this part of the circuit so that those high frequencies get shunted through the capacitor, and therefore we lose that leading edge there and round off the output signal of the oscillator. Over here, we want to get rid of frequencies below the cutoff frequency. So let's look at what happens at low frequencies over in this point. So we want the capacitor to be blocking low frequencies. So at low frequencies, that capacitor is going to look like an open circuit. If we made that parallel, what's going to happen? Let's put our resistor here and our capacitor, which at low frequencies looks like an open circuit. So there it is. And so we want to block those low frequencies, but yet they're able to go through this resistor here. So our low frequencies, some of them go through that resistor and are able to develop a voltage here. So we're not completely blocking the low frequencies. Those low frequencies will tend to round off this edge here. And with the low frequencies making it through, it might not even oscillate. And if it does, it's going to be more dependent on the other resistors and capacitors instead of this filter circuit. So we don't want the capacitor in parallel here, because when it becomes an open circuit at low frequencies, the low frequencies can still get through that resistor. So we really need to have them in series in this part of the circuit. So now when this becomes a open switch at low frequencies, it blocks the low frequencies. So low frequencies, if we look at a graph here, the low frequencies are blocked by this capacitor. The high frequencies are blocked by that capacitor, and only frequencies very close to the cutoff frequency are able to make it through. Also, if we reverse these and have them in series here and parallel there, what we're going to essentially do, because if this is in parallel, some of the low frequencies make it through, so that's going to kind of do that to the curve. And if these are in series, some of the high frequencies are going to make it through. That's going to do the same thing there. And what that does is it changes our filter from a high Q, which means a sharp filter that rejects high and low frequencies, to a low Q that's not going to reject the high and low frequencies as well. And so it may not even oscillate. It's going to tend to square off the waves. And also, since it's not such a high Q, the frequency may tend to drift around. So that's why we have this particular configuration in that filter, why it's series here and parallel there. So there we have it. That acts as a bandpass filter that has a fairly high Q, so very narrow bandwidth, so only frequencies very close to our cutoff frequency can make it into the amplifier. So even though it's very fiddly to get the gain just right, if it gets close to saturation, what that's going to do, it's going to introduce odd harmonics. Those harmonics are frequencies above our desired frequency. They come through here, they will not make it through this filter, and so they don't get amplified. So out here, we'll put a coupling capacitor there. We're going to get something that approximates a sine wave. It's not going to be perfect, but it's going to be pretty close. And the nice thing about a Wien-bridge oscillator is that it works over a very wide range of frequencies, and we can control it by, well, let's say we have a couple of ganged variable resistors here. Those are ganged together, so that means they work in unison. We can turn those resistors, and that's going to change our cutoff frequency. That changes the frequency that this operates at. And we can do that over a very wide range of frequencies. In fact, Hewlett-Packard got their start making a Wien-bridge oscillator that went on the desk and was used as a test tone generator. So there's the basics of the Wien-bridge oscillator. Of course, they can also be made with an op-amp. A lot easier with an op-amp, really, because you don't have to fiddle around with those transistors so much. But here's a circuit with an op-amp. I don't want to try to draw that off the top of my head. Here's one with the feedback diodes to help control the gain so that we get a good sine wave out of it. So that's the basics of the Wien-bridge oscillator. Why is it called a Wien-bridge oscillator? Because if you draw it right, you have your amplifier in the middle of a Wheatstone bridge. Basically, we have an astable multivibrator with negative feedback and a filter on the input to filter out unwanted frequencies. And we take some measures to control the gain, because you have to have the gain at exactly 1 for it to work. And if you get greater than 1, you're going to get square waves. If you get less than 1, it's just going to stop oscillating. And of course, if an engineer is designing one of these, they probably would not figure out everything. They would go to a design book to get pre-figured out parameters and pre-working circuits so they don't have to reinvent the wheel. So if you want to help other people find these videos and learn electronics technology, please give me a thumbs up down below. It really helps the channel. Don't forget to subscribe and hit that gray bell when you do so you get notified when I put up new videos. If you want to learn electronics technology and perhaps become a certified electronics technician, or just get a jump start in your studies in electrical engineering, or just learn because you want to, you can go to vocademy.net and take my free course. To help me put these videos online and keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support, and be sure to look to see what benefits you get for pledging and helping me put these videos online and keep Vocademy free. A big thank you to my patrons and other donors. Couldn't do this without your support, and thanks to everyone for watching.